modeling the production of electricity in Malaysia using Arima model.
Without even noticing, our daily lives heavily depend on electricity. Electricity is a crucial aspect of modern living. In the kitchen, for example, electricity powers most appliances including stoves, rice cookers, chillers, and toasters. Additionally, electricity provides power for a variety of entertainment and communication devices, such as televisions, radios, computers, and cell phones. In fact, today's communication and entertainment would be unthinkable without access to reliable electricity.
To understand Malaysia's power consumption, research was done to find data on the generation of electricity. The data series obtained from the Department of Statistics Malaysia represents the monthly rates of change in the production of electricity. The production levels are denoted by index levels, or percentage change relative to a base year. The data used in this study consists of 120 observations starting from January 2010 until December 2019.
A time series of the data was plotted to analyze its behavior. The original data time series shows an upward trend, indicating that the production of electricity increases over time. Seasonal component clearly exists, with the pattern repeating every 12 months. It is difficult to confirm the existence of cyclical components, so it is assumed to be absent. The series also has an irregular component, with a significant turning point when t equals 72 due to an update in the base year for the index of electricity.
After obtaining the data, the Arima model can be constructed. But what is Arima? Arima stands for Autoregressive Integrated Moving Average. It is a statistical analysis model that uses time series data to better understand the dataset or predict future trends. An Arima model can only be formulated when the stationary assumption has been met. In this formulation, it is fundamental that the series firstly needs to be differenced in order to achieve stationarity.
To start modeling, the original data was investigated for stationarity. This is done by plotting its autocorrelation function ACF and partial autocorrelation function PACF. The ACF shows a slow decay, and the PACF consists of several significant spikes. It is clear that the data is not stationary. Therefore, seasonal differencing was first performed to eliminate the seasonal component from the original data series. The figures show that the data is still non-stationary. Hence, the first order of differencing is performed. Now the data series is stationary.
Since the stationarity assumption has been met, the model can be identified. The general model will be in the form of Sarime PDQ, capital P, capital D, capital Q, N. The S at the beginning stands for seasonal component and the N stands for the number of steps in the seasonal period. P stands for the seasonal and non-seasonal autoregressive order. D stands for the seasonal and non-seasonal difference order. And Q stands for the seasonal and non-seasonal moving average order. Counting the number of spikes in the previous figures, the order for P and Q can be obtained. Hence, the identified model is Sarima 21211112.
Along with the identified model, two other models were proposed to be estimated and validated before choosing the best model fit for the time series of electricity production. The three proposed models are as shown in the diagram. These models underwent parameter estimation and model validation using the Minitab statistical software. To identify the best, they were compared according to the mean square errors, the chi-square statistics, and model specificity. For all three models, the residuals are white noise. Hence, all of these models are well specified. However, the best model selected has to be Model 3 because it has the smallest mean square error.
The selected model can be useful to predict the future demand for electricity. Malaysia has seen a huge increase in electricity production since the end of the coronavirus lockdown. It is important that the government and related parties prepare for the upcoming electricity demand. Since Malaysia is considering the implementation of renewable sources for future electricity production, it is necessary to have the ability to predict the forthcoming demand of electricity in order to supply sufficient renewable energy.